Hello, let's solve problem number 2081, sum of k mirrored numbers. So the problem statement is quite straightforward. We want to sum the first n k mirror numbers. And what are k mirror numbers? A k mirror number is a number that is a palindrome, if you will, in base 10 and in base k. So for example, in base 2, 9 is written like this, because this is 8 plus 1, and this is in base 10, this is a palindrome, and this is in base 2, and it's a palindrome as well, because 1 equals 1 and 0 equals 0. And we want to find the n smallest k mirror numbers. And the first thing we could think about is to brute force all the numbers from 1 to infinity, and we just stop whenever we find the first n numbers, right? And because n is smaller or equal than 30, then it could feel like it is possible. Fortunately, if we look at example 3, with n equals 17 already, the 17th smallest 7 mirror number is something along the line of 6 times 10 to the power of 7 already, right? And that's basically how many operations your computer can do in 1 second. So if n equals 30, then the number will be much bigger, and so clearly we cannot just look at all the numbers one by one. So we need to be a tiny bit smarter about the way to solve the problem. And the main idea is that if we look at all the numbers one by one, there's loads of numbers that we're looking at that aren't worth looking at all, right? If we look at numbers with 3 digits, how many of them are palindrome in base 10? How many of them read the same both forward and backward in base 10? So in length 3, we have the first one would be 101, the second one would be 111, then 121, etc., etc. But you can basically see that we're not looking at 102, 103, 104, 105, etc., etc. So if we only look at those numbers that read the same both forward and backward in base 10, we end up looking at so many fewer numbers. And because we're looking at far fewer numbers, then we'll just go a lot faster. But we still have, for each of those numbers, check whether or not it's a palindrome in base k, right? It's just we're not iterating through all the numbers that exist between 1 and infinity. We're just iterating on all of them that are palindrome in base 10. So hopefully far fewer numbers, and hopefully it'll be much faster. So the code will look like something like this. We'll keep the sum of the n first numbers in a variable. We'll just count how many we've seen so far, and we just want to do something like while true for I in self.magic function to get base 10 mirror numbers of length j, j being a variable that we'll initialize here. If self.magic function to check if palindrome in base k, give it the base and we give the number, then ounce plus equal I and count plus equal 1, and then just if count equals n, just return, and then after that loop we just add 1 and we check for numbers with an additional digit. So the main function is I think very understandable. Now it's just the whole challenge is just to code those two functions. And we can start with this function because I think it's a very simple function to code. Def So this function will return a boolean and we'll just convert the integer I in base k, and then we'll check if it's a palindrome by just checking the first digit with the last one, then the second with the second to last, third, etc. etc. So the first thing to do is to convert I in base k. We'll just use a list of integers and we'll do something like whilst I is bigger than 0, num digits dot append I modulo k, which will be the last digit in base k. So for example, if we're in base 2, the number could be this, and then modulo 2 will be this one. Then we need to get rid of this, so we'll just divide I integer division k. Then we'll have this modulo k will be a 1. We append, we divide, we have this modulo. The modulo separation will get us 0. We divide, we get 1. We divide, we have 0. We exit the loop. Very standard operation. And now we want to know if the number reads the same forward and backwards, which we can just return num digits equal num digits reversed. Now for the slightly more complicated function, this will return all the base 10 mirror numbers. And so this can just be an iterator of integers so that we can just iterate on it. So instead of return, we'll just yield everything we can. Very simple case would be if length is 1. Because if length is 1, we can just return everything between 1 and 9 included. Because if there's only one digit, then it's obviously reading the same forward and backward. Now, if the length is not 1, we basically can have whatever we want in the first half, but in the second half we're constrained by what we had in the first half. The first digit can be whatever between 1 and 9. From the second digit to the middle of the list, and this not included. We can have anything between 0 and 9. It's just the first digit couldn't be a 0 because we specified a length. If length is odd, then there's a number in the middle that doesn't have any constraint as well. The digit at index and then from length over to +1 to the end, we have no choice but follow the first half. So, give you an example. If length is 3, from 0 to 3 divided by 2 equals 1, 1 excluded, so just the first digit we can do whatever we want. The second digit is in the middle, so we can do whatever we want as well, because 3 is odd. And the third digit, so index 2, we have no choice, we have to copy whatever is at index 0. Right, now, so that's just the logic behind it, we just have to code it. So we'll just, again, have a list of integers, we'll call this num digits. Initially we put zeros everywhere, except for the first digit, and obviously if we change the first one, we have to change the last one. Since this is already valid, we can just output the number. Right, so we would do something like yield num digits. The problem is num digits is a list of integers, and we want to output integers. So we need to have a function that transforms num digits, which is a list of integers, in an integer. We also need to take care of this, because if length is odd, then we have to allow this digit in the middle to be anything. Right. So we'll just say something like for integer in self dot magic function to transform num digits. We'll give it the length, and we'll give it num digit list. We'll just yield integer. And so we just have to code this function. And so the first thing we can do in this function is to check if length modulo 2 is 0, then we don't have to worry about this, so we can just yield num digits as an integer, not a list. So the way we can do this is int dot join map string num digits. So what am I doing? This is transforming my list of integers to a list of strings. This is transforming my list of strings to one string, and this is just transforming the string to an integer. Now, if the number is odd, we need to iterate from 0 to 9, 9 included, change the number at length divided by 2, and put k and yield this. And so that at the end of the day, if length is odd, then every time we call this function, we return 10 numbers, otherwise we just return one number. And so now, where are we? We have a number that would look like this, and we are returning, maybe the series, and we are returning this one, everything all the way up to this one. But we also want to play on those three, which will influence those three, to return all of the base 10 mirror numbers, because this is what we want, this is what the function should be doing. And we also want to return them in a sorted manner, right? So we are indeed starting with those ones, but the ones after have to be those ones. Because at the end of the day, we want the n smallest ones, and we stop when we have n, so this has to return everything in order, right? So this is why we have to basically transform this 100 into 101, 102, all the way up to 999 in this very order. And the reason why we only care about the first 3 digits for the order is because when we are comparing two numbers, the leftmost digits have the most importance anyway. So I will have a pointer here, and I will change this digit, and when this digit is a 9, I'll just move the pointer here, and I'll change these two, and then when these are 9, 9, I'll put the pointer here. And whenever I modify something at a pointer position, I have to do the same at length minus pointer minus 1, right? Because if the pointer is at index 0, I also want to change length minus 1, which is the last element. So I also have to keep this in mind. So let's initialize the pointer value, which will be right before the middle. We take my example back. We're initializing the pointer here. Here length is 7, 7 divided by 2 is 3, 3 minus 1 is 2, 0, 1, 2. And as long as we can, if the number at pointer, sorry, it's not number, num digits at pointer is not a 9, this is very easy. We just increment the digit, we increment the one at the other side of the number. As we said, this is very important, otherwise it's not a mirror number. And we just output everything. Am I doing this correctly? Yes. Yes, and we output all the valid numbers. Now, if the digit is a 9, that's the slightly complicated part, because we need to move the pointer around. And the thing is, we don't know how much we have to move the pointer, because if we are in the case of this, etc., etc., maybe our pointer's here, and we want to put the pointer all the way back here. So it has to be another while loop. But those while loops don't cost much, because we're basically just, this list just has log of the number we're looking at elements, which is a very small. So we're very happy about that, because we don't have to spend too much time moving this pointer around, is what I'm getting. So whilst numDigits pointer is 9, and obviously the pointer is still a valid pointer. This is important because maybe I'm at the number like this, and after this loop, maybe my pointer will go to -1. So if my pointer ever goes to -1, I just return, I've done everything. So this condition too is important. And that's a big or equal, obviously. If pointer is 0, that's still valid. It's only when pointer is -1 that's not. And so what I do? Well, I just simulate an addition. It just means that I'll put all the 9s to 0. Their counterpart will go to 0 as well. And I move the pointer to the left. And when I'm done, I just add 1 to the first one that's not a 9. Obviously, if pointer is -1 at this stage, I just break. Just finish. I could actually just return as well. Obviously, whenever I change the prefix part of the number, I also have to change the suffix part, but that's easy because it's just symmetric every time. And then again, I can yield because I found new valid base 10 mirrored numbers. Numbers plural if length is odd, only one new number if length is even. but this function just takes care of it, and that's why I abstracted this in this function, so that we don't even have to worry about those two cases anymore. And what's important is now I went from maybe this to this. The problem is my pointer was here, and now my pointer is obviously here. I want to put back the pointer here after changing everything to 0. So I just have to do something like pointer back to length divided by 2 minus 1, which was its initial position. And this function should allow iteration on all the base 10 mirror numbers in sorted order. And because I'm calling this function on length equals 1 plus then length equals 2, then length equals 3, etc., then I'll just end up iterating on all the base 10 mirror numbers in a sorted manner. And I'm just realizing I have to start with j equals 1, obviously, not j equals 0, because there's no number with length 0. And so that should be it. There's probably loads of typos. Let's check the test cases. The cases seem to indicate that the code is correct, and we can just submit. And that works.